Any further questions for the speakers, Chair? Or the audience?
I am.
Well, the question is, given that you have to deal with aleatory uncertainty and also epistemic uncertainty, that's the rub, right? It's the epistemic uncertainty that's causing the problems today. And the Monte Carlo is perfectly fine for aleatory by itself. Everyone agrees with that. The question is it sufficient when there's also epistemic uncertainty? Does it give you the right answers? Does it give them to you in prime time? That's the question. That's the question for the discussion.
Simon, I think you wanted to. I was going to make a point so far that when we've been discussing, particularly in the kind of expert elicitation aspects and the other ones, we're quantifying uncertainty. We've been typically looking at scalar quantities, or when you're expert elicitation, you're kind of, what is my uncertainty on this thing, this scalar value? You're drawing a distribution. So a scalar value, so a singular value of something that is uncertain. The reality of a lot of the things we deal with, they are not scalar. The uncertainty is a function of something. So an example is CFD. The CFD model form uncertainty isn't a number. It is a variation over MAC and over angle of attack and other things. So the uncertainty is a distribution over different operating conditions of that model.
The distribution is stochastic sense or?
No, function is probably better than distribution. A function of its operational conditions. And this is typical of the sorts of uncertainties we look at when we get into the details. When you start diving into your detailed models, uncertainties are not a singular value, they are complex things. So one of the challenges we've had when we started looking at expert elicitation techniques, how the hell do you deal with that? It's hard enough coming up with a probability distribution from an expert of a scalar. How do you define that as a probability distribution over a function of different things? Not an easy question. But that's a real challenge.
And I presume that what that means is you know what the technology is.
Again, we have an idea. We know CFD is more uncertain in the transonic region. But there's what is the relative uncertainty in that region to other areas is again an expert elicitation guess. So how many parameters do you need to describe an uncertainty that is a function of a number of operational conditions? Is it a single uncertainty parameter when you assume a relationship, or do you have an uncertainty on the relationships as well? It's more involved question. Does that make some sense?
Yeah, it is.
It's a twofold. How many do I need?
But I believe that at least for CFD, the questions are unanswered, in my opinion.
Yeah.
When you did your expertise in elicitation, did you actually manage to go anywhere, or did you completed the process, you end up with a result?
Yes, so this, Chris Linus, who's still on the call, was involved in it. I wasn't directly involved in this with Mr. Cook. So it was more a practice exercise. So it wasn't a real industrial question, but it was trying to understand. A result did come up, but I think it's probably, Chris is still there, but
I am.
Oh, hello, Chris. What was your summary of the experience of the kind of Roger Cook expert elicitation?
It was very nice to have something that had an explainable and defensible mathematical justification behind it. Which was, I think, valuable when we were explaining to people what we were going to do, and gave them confidence that answers that they were giving would be taken seriously and treated. I think it was in your presentation, but it's, you can show that things are neutral. The big problem that we had was getting the right calibration questions. Because if it's something that we were dealing with, things where the body of knowledge is in some ways quite narrow. The things we're interested in are things where if someone goes to the right area of our drive, they can probably just find the answer, which means we're interested in them doing calculations for things where the answers haven't already been done, but then they'll probably use methods which we would probably use to solve the problem. And so the issue was, if you've done all the calibration, you've probably put in enough effort to just answer the question. And that was the tricky bit. But as a process, it seemed to be very good. If we could solve the calibration question problem, it would be probably pretty realistic.
Thanks, Chris.
What's the level where you see the expert coming in? I mean, you can take the expert and the solicitation on the level of range equation and assign distribution to the range. You can take the expert solicitation on the number of volumes you have to put in a grid to run a simulation. So all of that has uncertainty to a certain extent. So where is the added value of putting expert opinion in, and where it's simply extra effort that probably does not have a benefit?
Question?
All right, fair enough.
Yeah, I don't need to move the mic for that. No. Okay. Can I ask you a question then? So in the past, you've expressed, Simon, you have expressed a doubt that intervals, despite their nice mathematical objects, can be used in what you very often deal with, trait studies. Can you comment on that? Why do you think this is the case?
Maybe it's my lack of knowledge. I don't know. I don't know. It's maybe a feeling. Maybe I need to know more and get better knowledge of how these can be applied. But typically when we're dealing with kind of trade spaces and uncertainties, we're looking for these kind of trends. So we're looking at relative confidence. We're not looking at absolute kind of safety. We need to be out or within a kind of limit of confidence or whatever else. We're looking at the relative confidence and the relative tradability of multiple different objectives a lot of the time, not all of the time, but a lot of the time. So traditionally we have used more continuous probability distribution type approaches, back with surrogates and Monte Carlo propagation. Just my experience. Others have other experience. But this is where I'm typically coming from. So I'm very open to the ideas of alternatives, but not yet seeing how I can use it.
Okay, that's very interesting. Thank you.
So Alex and Andrew both described distributions used to characterize epistemic uncertainty about a single value. And Peter at the beginning was suggesting that that's somehow wrong, that if it's epistemic uncertainty, that means intervals. You ought to use bounding methods to characterize what you don't know in there, because after all, if you don't know the distribution. And several people have suggested that you can't just put in distributions and act like that's a proper characterization of epistemic uncertainty. Alex sort of shows that with the contraction of the uncertainty in his first slide. So the question is obvious, right? So is it legitimate to use distributions to characterize epistemic uncertainty, just the naked lack of knowledge, as opposed to the aleatory uncertainty, which is the wiggling of the numbers, right? Clearly, everybody agrees that you can use probability distributions, precise probability distributions for aleatory uncertainty, for the wiggling. The question is it okay to use them when that's not the case, when it's just naked ignorance?
But it's not always naked ignorance. So when I've used it for epistemic, we've kind of we've fit with triangular distributions. We know the mode and we know some extremes. So we know it's more likely to be in the middle, and we do know that. So this is a kind of, again, an input knowledge. I know it's not equally valid. I know we're more likely to be in the middle range, and these are my limits. So we've typically categorized that with, okay, a triangle is probably as good as we can get.
Constants you were estimating, or
Distributions. So no, so scalar value,
Scalar value.
a probability distribution of a scalar value. So yeah,
but that seems to be, that's what Andrew and actually Alex were also suggesting, that they could be used for scalars. Apparently, yeah, is that right, guys?
Well, precise distributions.
Yeah, precise distributions as a way to, well, confidence structures, for instance, precise distributions sometimes for scalar values, or constants. That seems to be okay. Anybody object to that?
Given the requirements of the confidence distribution, that is a valid, or it's valid under a particular interpretation of probability.
Is it okay to do?
I mean, that's the thing. It's like you can use that level of knowledge and propagate it through, and you have answers that will be valid conditional on the what you put in being true. And then it's the fact that maybe then, yeah, you can, if you've got the capability of doing so, you can look at sensitivity analysis of, okay, well, if I change my input assumptions, like how does that actually affect, like I might not actually have a clue what these inputs are, but I have some feeling, and then I can kind of wobble the edges of those feelings and see how that affects the output. It's not probabilistically like concrete, but it gives you a tool to kind of prod at what you're working with.
Okay, what happens if it was a normal? I kind of put a normal or a triangle. Does it change my answers? Does it change the decisions I'm going to make? If not, then it's okay. If it does a bit, then you know it's almost the uncertainty on your uncertainties. You do a secondary sensitivity study on your assumptions, and it's just like, yes, I've got enough confidence that they are good enough, or I have nothing better.
P-box analysis can be useful for assessing all of the distributions at the same time. Given, because you can generate a P-box given the constraints of knowledge that you have, and just do it all through the P-box rather than testing different distributions.
Yeah, true.
I think that puts us in a very nice position to really say a couple of words about the real modeling problems that all engineers have, and that's black box models.
Yeah.
I mean, we mentioned that more than once. You mentioned something very interesting. What do you do if it's a black box or if it's a gray box? So how often do you guys, everybody here, work with a crystal box or a gray box model? That's something that we could do a lot about in the way of uncertainty.
Can you define what's your definition?
Right. Okay. Yes. Yes. So in terms of definitions, obviously we have the open source. You can double with the code. You have crystal boxes whose code you can't change, but you can see it. You know what's happening, but you can't change it.
Yep.
For example, it's too expensive. You don't know how to do it. And black boxes, true black boxes, you know nothing other than the input and output. Okay. So what do you think about this? Because there are certain tailored methods to propagate epistemic uncertainty from within p-boxes and intervals optimally if you knew what you're dealing with. Not necessarily change the model, not necessarily in an intrusive way. Any comments?
So it's a lot of our methods and not a single piece of analysis code, and that's probably where it is complicated. So there are lots of different analyses. So Nastran, okay, Nastran destructive analysis, it's a semi-black box. Well, it's black box, but you know the methods inside. If you detailed into the structure and finite element methods, you know the breakdown. But actually, when you build it together to the structure, the uncertainties are not on the details of the method. It's how you put the model together. Usually, not in the details of FEM methods. But when you're doing a full calculation, you're pulling together or combining very different models, a CFD model, a dynamics model, a structural model, a systems model. There are multiple different models in each part of the process.
It's the outputs of one form the inputs of another.
Yes.
So do you project what do you project from the outputs? Point estimates? Do you project the whole distribution? What about the dependencies?
I think we do. I haven't done a lot of detailed, I would say, uncertainty around MDAO, which are the detailed level around multidisciplinary systems. This is a separate topic we're getting into, I would say.
But is it safe to say you generally ignore the dependencies that may exist? Or is that unfair?
No, that's with DAWS, at least in the NDA scenario.
Correct.
So We tried a bit. Let's stick with the fluid structure as example. It's probably the easiest. So aerodynamics coupled with some structural model. CFD was probably Nastran or something like this. Then they have a tight coupling to one another. But the coupling are field variables. So it's distributed forces to distributed displacements. Now, the most simplistic approach that you can do, and that's probably what's currently been done, is you see this as one bit. So the CFD and the FEM becomes one, and you propagate some inputs that affect both to a joint output of both of them. So let's say you do some sizing in between, you get a mass. That's a scalar at the end, and you have some aerodynamics and so some Mach number and some thickness input or something. Then this becomes one. If you try to take them apart, then it becomes significantly more complex because it's no longer aerodynamic, passes one scalar value to structures and back. But if you take them apart and then you pass point estimates on, the result is, I don't know, you get something, but it's probably garbage.
Right. But that's because you said they were components. So in this case, they're unified, right?
So this is a different way of how you could propagate uncertainty around a complex, tightly coupled set of analyses or analysis functions. So what Philip was suggesting is the typical way we would do it if we have to is you run the chain of analysis functions deterministically, but you input those in each one of those deterministic bricks. You might say, okay, I have an uncertainty in my aerodynamics module, on my structure model, and you inject random draws of that in a Monte Carlo type way into each of those, but you're running the chain towards. If you separate them out into individual codes, it becomes very difficult because the interfaces are these complex fields, and dealing with that is very difficult. So this is the uncertainty on complex multidisciplinary models that we use in aircraft is a complex topic. And I'm not necessarily an expert on that in detail.
So it's not impossible, but it's just really complex.
Yes.
Because it sounds to me really hard to digest the fact that you have something assembled by people, and it's clearly component-based assembly, right? You have an aerodynamic solver, structure solver, that you shouldn't be able to pull them apart. You should be able to, but it's just a complex thing that you have to deal to establish the interface. Because how did this?
You're doing the tightly coupled national strategy, you're doing the sort of the FE,
Okay.
etc.
Depends on the problem.
Yeah, it depends on the problem.
Different
But
problems
at the end,
separate them.
you say, okay, you know, I'm sampling from these random.
That's right.
You sample from all these random elements, and you get a point at the end, be it like a CL or a drag or a deflection, and you've got to do that lots of times to get your distribution.
Right.
Where, yeah, I mean, that's why I'm struggling a bit this afternoon, that you say, oh, I got this distribution and this, and so seeing some examples of what was shown would be, yeah, nice toy problems would be good.
But isn't even the complex codes, PDs, let's say, you know, that's probably the deepest my understanding goes in complexity. Aren't they even just a bunch of elementary arithmetic operations at the computer chip level? So where does the complexity? I mean, if theoretically you could pull it apart in terms of binary operations, which is not feasible.
Code, well,
Yeah.
the code itself.
Yeah, but that's not feasible. Obviously, we've agreed on that. So what is the difference between fully coupled, tightly coupled simulations and loosely coupled, so that you can't pull the tightly coupled apart and still get the same answer? If you were, you know, if you would go down to the computer level, what prevents you from analyzing them separately? Isn't there absolutely anything that you can do to port the results from one to the other through an uncertainty interface almost? If I'm making any sense.
So what do you, it depends what you mean by separating them. So separating them, maybe you say you could run an isolation of your all of your aerodynamic analysis. Okay, I have uncertainties on my CFD, mesh size, uncertainties on whatever geometry, whatever else, and you run that in isolation. So okay, I'm going to run an uncertainty study on that, and here is now my outputs that are now uncertain. Those outputs are now not a nice scalar number with a probability distribution.
Right.
Those outputs are pressure distributions as a function of Mach, CL, blah, 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 with an uncertainty band. Okay. So then the modeling of that is how do I propagate that to inputs of another process,
Right.
You could take the same, almost the same for design of experiments and say for each one of those draws of uncertainty, this is my correlated effect and feed it to the next one. Or you could try and break it down and model again, this is the variation I see at that interface. I could remodel the uncertainties of that as a different formulation.
Right.
So the problem I've said there is we start off, okay, we make draws on all of the uncertainties and we're propagating it because the breaking down the interfaces is difficult.
Oh, it's because when you modify the flow field, that modifies your structure, that modifies the flow field, that modifies.
Yes.
I understand that, but yeah, okay, so okay.
There's a tiny couple of things that you won't get. There's a couple of things you guys start for, so you get the solution. But you could do a Nastran type of couple and then separate what's the structure and what the aerodynamics is doing.
That is what I'm referring to. So
But you wouldn't want to do that.
Yeah, theoretically, you can't
Yeah.
do that. No one stops you from
Yeah.
doing it. It's simply infeasible by the compleximal effort you have to put into this. So
My question was, that is how much of the output is actually transmitted to the
input of the next model down the thing. Well, I mean, is it point estimates? Is it full distributions? Is it the full joint distribution with the dependencies? Or does it, I assume it varies maybe for different problems, but
there is currently only deterministic version of the coupling at the end of the day. So you pass the point estimate, but it's a field of values.
okay, so field of determinants.
A field of deterministic values ranging between 10 to 20 up to millions.
So the answer is point values, except there might be dependency.
Correlation within a specific.
Correlations in that structure.
it's functional dependence, I suppose, within the field. Yeah, not the field dependent type.
But not
Okay.
stochastic.
Not a stochastic dependence, no. So Simon, that's what you think prevents you from going the crystal box way, where you look at the model without modifying it, but looking at the model and say, oh, okay, maybe perhaps this is a monotone relationship where I can just put the endpoints of an interval and get an interval out, and I am sure this is the rigorous result, as opposed to a highly nonlinear function where everything just gets crumbled.
Kind of make sense. It depends what types of models we're looking at. So if we look at early design phase, which I'm not the expert at, some of us on the call probably are, the models you're modeling in the entirety of the aircraft system. So all of the mission optimization, the weight optimization, low level of fidelity, but you're modeling everything. So there's a lot of complexity and dependency. It doesn't mean to say that engineers can't write down every one of those equations or understand all of those, but there is quite a lot of them. So you could take the time to break all of that apart and actually go more intrusive. There'd have to be a good reason to. It's not necessarily impossible in some of the simpler methods, because there's nothing, I guess, inherently complex, like it's not a CFD simulation or whatever else. They are simpler equations, but there's just lots of them with lots of dependencies that go round in a computer to optimize and converge on things.
Right.
Okay?
Right. Yeah.
So you could pull it apart, but why? As an initial question, what do I get out of it?
Can I contribute to this?
Yes,
I
of
mean,
course.
if your question is, you have uncertainty about the modeling of an aerodynamic effect.
Yeah.
Okay, that's your question. What's wrong with propagating that particular uncertainty through the model, through the aeroelastic model, to the point at the aircraft level that you're interested in, the dynamic stability?
Yeah.
That's the metric you want to find. That's fine. You could do the same about uncertainties in the structural model. And you could do the same about uncertainties in the coupling. But there's nothing wrong with doing them independently. And aren't those the questions that you're likely to be asking? Or if you do have uncertainty in the way you've taken care of the Mach number effects, the rotor blade goes from Mach numbers of almost up to the speed of sound at the tip at high speed. So you've got to have a lot of data to populate that model, and there's uncertainty in that data, in the way you gathered it, whether it's through CFD or wind tunnel tests. So you can do that independently, and there's a good reason for it. If you load your uncertainty in that particular area, isn't that the reason you do it? I'm happy with the Nastran model. I'm happy with the modes that I'm using. It's all linear structural stuff. It's just the non-linearities, supersonic flow, transonic flow. That's the bit I'm uncertain about.
Yep, and if it depends on the problem and on the metric. So if you're interested in a particular instance, which is the aerodynamic uncertainty, so bearing in mind that ultimately we're interested in performance metrics that sell the aircraft or certification requirements. How much fuel do we burn? How heavy is the aircraft? Does it make its takeoff field length requirements? These are the things that matter ultimately, but the way those are calculated goes into a lot of detailed physics models that interact, come up with those final metrics that we're interested in, okay? So if you're dealing with an uncertainty in your aerodynamics model and it is purely tightly coupled to what is the uncertainty on my drag prediction, you're talking about the specific drag prediction at a point, then yes, you would run that independently. And go, okay, I've got uncertainties in that, what is my prediction?
Whenever I talk to aerodynamic colleagues, they say, well, what really is the drag? They just laugh. It depends on what turbulence model you use and all these other things. I was sort of like that, you'd be saying, right, where's the shock position, for instance? That would have a big effect.
That's what you're interested in, then you're putting in one model. If, however, you're interested in the aerodynamic pressure distributions are also uncertain, so not just drag, but as a function of that drag, the pressure distributions are uncertain. Those pressure distributions contribute to the loads, which contributes to the sizing, which contributes to the weight, and that ultimately has an effect on the fuel. There's the weight through all of that chain of processes, and that is a very complex chain with lots of uncertainties in each bits of that process. Does that make some sense? I'm not sure I'm answering the question.
I think it strongly correlates to one of the questions we had before. It's like at what level is uncertainty quantification and this forward propagation actually beneficial, and at what point isn't it beneficial? And I think we haven't found an answer yet.
The benefit of uncertainty analysis is so you can get rid of safety factors, right? And so you can realize the uncertainty. I know you don't want to admit it, but that's why. Look, it's not just engineering, but all fields are going. The transition is happening between standards-based rules and performance-based rules, and the performance-based rules are all expressed in how sure are you that it's going to stay up and do the job. And you can't get there except through uncertainty analysis. Just as your certification by simulation, certification by analysis. Before it was ASCII, we were certifying this nuclear stockpile by simulations, and it turns out, by the way, the stockpile gets less uncertain when we turned off the testing. So just so you know, that's right. That's what we should all be afraid of. But this is the benefit of uncertainty analysis. So we can replace the over design that's built into engineering with a more appropriate design that's cheaper and better, but just as reliable. That's what we're all headed towards.
Something by doing an uncertainty propagation for a drag coefficient and for a mass, then do the range equations and do the same for my constraints. And I don't have to touch the underlying fluid structure couple level to do that. So I can treat certain bits as black boxes where I propagate input to outputs.
I think that's right. And the benefit of having safety factors and uncertainty analysis alive in the same
Scheme is that some things you can't do the uncertainty through. You have to treat them with safety factors, right? But other things you can exploit the economies and tease out some efficiency that was not otherwise achievable simply because you were doing this, blinders approach with safety factors. That is the benefit, right? That's what we're all subtly talking about, but not admitting.
No,
Engineers, the most conservative, but
If you can use it, if you can exploit it to benefit like exploratory design and things, like build up a base of people realizing some benefit from this in a case where it's a bit safer to do so rather than trying to kick out safety factors.
Right.
Build up trust in the system that way, and then
Right,
maybe
right.
if it once it's
That's
mature enough
the
through that.
strategic thing to do, of course, because as Sean was saying, trust is very,
Yeah.
hard won and easily lost, right? So God forbid you lose this trust by over applying uncertainty analysis in places where you shouldn't be doing it, or making assumptions that are ridiculous on their face, like everything's normal and linear and independent and stuff, and getting wrong answers. That's why we're trying to be really careful about this epistemic uncertainty business, so we can do it right and not have to pay for the transition between safety factors to uncertainty analysis with fatalities.
Challenging safety factors will improve engineering design, or potentially. One thing, what I know for definite is if you remove the safety factors, the cost of designing and certifying an aircraft will significantly increase. So you will have to do a huge amount more analysis, a huge amount more testing, and a huge amount more validation. We may get a benefit. And that's I have a definite, it's going to cost a shitload more. I'm going to go with that. And a potential benefit. That's not a good thing, easy thing to sell. But
obviously it has to be piecemeal, finding the local victories where there are to be had, such as I was suggested in design, where it sort of first shines and people can sort of get used to it,
understand what its weaknesses are, and what its benefits are. Because clearly UQ has to build that same level of trust or more, not just to replace safety factors, but to augment the whole field. Like the scaffolding has to be done very carefully, right? You remove the safety factors, but you still have them there while you're doing the UQ. Yeah.
So you would have to have a potential large amount of benefit.
in order to even try.
Well,
Oh, over design. There's a question. We still have aircraft failures. Aircraft will crash. People
that's
still.
just bad.
Is it? Debate. Depends on the consequences. So it's not like all aircraft you never see any incidents in service. There is still a level of course. But no, the reality is, your statement, aircraft are over-designed. How do you know?
You have like expected maintenance requirements. Not even looking. So, well, I guess crashes obviously as well, but ongoing unexpected costs. Maybe an indication of like there was something missing considered in the design, or like something unexpected came up.
In terms of the inspections of aircraft and cracks and propagations, things do break. When you get involved in the reality of what people do with their aircraft, you're amazed what some stupid operators will do with their aircraft and how they misservice them and how they drive them into lampposts and do all kinds of other weird things with them. So things happen in reality, and maybe the safety factors is, again, it's a comfort blanket. It is a comfort blanket, but it's also built in a level of robustness in the design to things that are unexpected.
Exactly.
That is beneficial. That, okay, we can absorb a lot of things we don't know and things that happen because we know the design is robust. And every time you remove that, it's like, okay, what is the impact of driving into a lamppost? Was it somebody forgot to put a parking brake on an aircraft and reversed backwards and it wrapped its wing around a lamppost? One example of something stupid. Do I have to design it for that?
If you're the one who signs with his personal signature in the end that this is safe, what information would you require from someone to account for that? So the unknown unknowns are covered from the safety factor, but at the end there is a person who puts his signature under this, and there was also someone who put a signature on the Boeing 737 MAX thing. He does not have a great life, so ask yourself, what do you require personally as an information to say, I weighed the safety factor and I'm still feeling confident enough to sign this, given everything you know, you don't know, and you can only vaguely imagine people doing with an aircraft.
And it's a good point that ultimately it's a person, so it's limited by how much a person can understand, trust, believe all of this and absorb all of that complex information.
It's usually unless it's
Who's also the chief engineer.